Here's a mechanics question, which is actually looking at the kinetics of two objects undergoing some form of constrained motion. So the accelerations of the two objects, as you'll see, are not actually independent of each other. And this is actually a hint that the question tells us, right? So this is saying that first establish the kinematic relationship between the accelerations of the two bodies. I don't know if I want to make this the first thing that I'll do, but we will definitely have to look at it to be able to solve the question. And this is the kind of question that you can get as a first-year engineering student, or you might even see this in high school in some cases. Now, actually, the first thing that I would like to do in this case is, before looking at free body diagrams and everything else, I actually want to examine this bit here, right? Because this is actually telling me that we know what this angle here is, right? So I'm going to call this angle theta. And then what this is saying is this angle theta would be the same as this angle over here, right? So if we have a right triangle, which has a side of 4 and a side of 3, you can actually find what the hypotenuse is using Pythagoras, and the hypotenuse will be 5, right? So this angle theta, which is this one here, we don't really care what the angle itself is. We just care about the sine and the cosine and maybe the tan, but sine and cosine is usually enough. So sine is 3 over 5, which is 0.6, and the cosine is 4 over 5, which is 0.8. So that's the first thing that I just want to get out of the way. So we can find the angle. It's about 37 point something, but the sine and the cosine are going to be what we're going to need further. So knowing this, I will then try to write the free body diagram of each object. So let's start with the simple one, which is the hanging mass. Okay, so the question actually wants us to calculate the tension in the cord. So wants us to find the tension in that cord, and also the acceleration of the heavier block. So we're going to start with the mass that's hanging. So we have this, and this is 15 kilograms. So let's add the forces. So we have, on one hand, we have mg acting down, and then we have tension acting up. And that's all there is to it. So the net force is going to act in the vertical direction, and I will say that the acceleration is downwards, and we can write Newton's second law, right? So that's the sum of forces in the y direction is going to equal to not 0, because we don't have equilibrium. It's just mass times acceleration, and I'm going to call this A2. So I'm going to consider this the second object and this one the first object. So this is MA2. Okay, and I think I should also call this M2 as well. So M2 and A2. Right, so the forces, and what I'll do in this case is I'm going to assume that going downwards is positive, and going to the right is also positive. Okay, so let's see what we are actually dealing with. We have one force acting in the positive direction, which is M2 times G. Then we have minus tension, and that is equal to M2 times A2. And we're done so far with the second object. So we have, we have two unknowns in here, so we can't really do much about it. We're going to leave this. So I'm going to call this equation 1, and then we're going to move on to the first object, to the block that is moving horizontally. So we have a block which is just sitting, and then we have essentially two forces acting on it due to the string. So, there's like a small pulley here of sorts, which I believe has no friction. So the question says the small pulley attached to the block has negligible mass and friction. This is very important. If this was not the case, the solution would have been, well, let's just say slightly more different. So we've got two forces acting on the block due to the strength. The first one will be acting downwards. So that would be, if I draw it on this diagram, it would be this way, right? So there's a force acting here, there's a tension acting here, and then there's another tension acting here as well. Okay, so that's the other tension, which is acting this way, and obviously they have the same value. And this tension is acting at that angle that we just found, which we called theta. Okay, other than that, we have the usual stuff. So we have weight. So this is going to be m1 times g. We have the normal reaction force. So I'm going to draw that here. And then we also have friction, right? Because in this question, we are dealing with friction. And let's think about how friction is actually acting. So the only force which has a horizontal component so far is this tension force, right? Which is trying to push the block to the left. So if the block starts moving to the left, or if the block has a tendency to move to the left, then friction will act to the right, like this. And this is the kind of friction which is kinetic. So this is going to be mu multiplied by n. Okay, so that's all we know so far. The first thing I would do in this case is I would look at the vertical equilibrium of this object, because this object is not actually moving vertically, so the forces acting along y, they balance each other out. So we can say that n, and then we have, so n is going up, but I'm gonna put a minus n because I kind of want to keep the same sign convention as here. So minus n, and then I have plus t, where t is this one, and then minus, so this tension also has a component going up this way. So that's going to be t sine of theta, and this will be, well, we're not done yet. We also have the weight, so plus m1g is equal to 0. And I think we're done with vertical equilibrium. So we can rearrange. So we have n is equal to m1g plus t times 1 minus sine of theta. And at this point, I don't really like using numbers in the middle of the question, but I will use the values of the sine and the cosine of theta. So we know sine is 0.6, 1 minus 0.6 is 0.4. So that's what the normal reaction force is, which means that the friction is, mu multiplied by that. So it's mu multiplied by m1g plus 0.4 t. So we have an expression for the frictional force. Okay, then I guess what we can do next is, I would say, look at the acceleration of this object, right? So I decided to use the right direction as positive, so I'll just stick to that, which is a bit strange in this case, but I'll stick with it and you'll see that we still get the correct answer. So we have friction, which is mu n, that's acting to the right, and then we have minus, so the only force that's going to the left is this component of tension, which is t cosine of theta. So minus t cosine of theta, and this is equal to m1 times the acceleration a1. Okay, so we know this is friction, which we already have here, so I'm gonna do the substitution. So we have mu, and then m1g plus 0.4 times t minus t times cosine of theta. So cosine is 0.8. So this will be 0.8 t is equal to m1 times a1. So that's it in terms of the equation of motion for the second object. So this is equation 2, and this was, I guess, equation 1. But we're not done because we still don't have enough information. So our three unknowns are T, the tension, A1 and A2. And we have two equations with three unknowns, so we need something more. To find the relationship between the two accelerations, we're going to use the fact, the obvious fact actually, that the length of the string is constant. So we're going to write an expression for the length of the string using the coordinates, the x and y coordinates of the two objects, right? So I'm gonna, I have my coordinate system starting from here. So the first part of the string is gonna be the hypotenuse of this triangle, right? And if you think about it, this hypotenuse is actually made up of you can actually use two sides, the two sides of this triangle, which is, one of them is x1 and the other one is y1, to find the hypotenuse. So that is the square root of x1 squared plus y1 squared, like this. Okay, and then plus we also have this vertical bit as well. And the vertical bit is given by the fact that this is what we call y1, and then we have y2, which is the y coordinate of the second object. So we have plus, and then we have y2 minus y1. And we're going to use the fact that with this expression, if we differentiate it, differentiating the length gives you 0 because the length of the string is constant in time. And also the first derivative with respect to time and also the second derivative with respect to time of y1 is also 0 because that block doesn't move up or down whatsoever. So let's take this and let's differentiate it twice to get the accelerations. So we have this, and then if we differentiate this once, on both sides we have L dot equals, and this becomes 1 over 2 square root of x1 squared plus y1 squared. So I'm differentiating everything with respect to time, and this is the square root, and then we differentiate what's inside the square root using the chain rule. So that's d by dt of x1 squared plus y1 squared plus, and then we have d over dt of y2 minus y1. Okay, so we know for a fact this is 0, and we also know this is 0. So what we're going to end up with is that 0 equals, and then we have 1 over 2 square root of x1 squared plus y1 squared multiplied with, again, this is gonna cancel out. So we have 2x1 times x1 dot, which is the velocity of the first object in the x direction, plus y2 dot, like that. And we can also cancel out the 2's like that. So this is 0 equals, this would be x1 over square root of x1 squared plus y1 squared x1 dot plus y2 dot. And then technically we have to do the same thing again. So this is going to turn into something relatively messy. So let's try to think how we can differentiate this again. I think I'm going to use the quotient rule for the first part. So if we do d by dt of both sides, I'm going to differentiate the top. So I'm going to put x1 dot here and just gonna remove this. So I have x1 dot, and then dot, multiplied by x1 squared plus y1 squared, minus, and then I have x1 dot, times x1 squared plus y1 squared, and then this is differentiated with respect to time, over x1 squared plus y1 squared, plus, and this is y2 double dot. Okay, so let's see what we can do about this. So this first term is another product rule, right? So this is x1 dot plus x1 and then x1 double dot times x1 squared plus y1 squared, and then this is minus x1 dot 1 over 2 square root of x1 squared plus y1 squared, multiplied with, and then we have to differentiate what's inside the square root, which is 2x1 dot. So this looks pretty messy, but something will simplify, because the question tells us something that's quite critical, and that's the fact that the system is released from rest. If it's from rest, that means that x1 dot is equal to 0, and also y2 dot is equal to 0 as well. So all the terms where we have x1 dot, we can just cancel them. So this goes away, and then this whole term goes away as well. So we end up with 0 equals, and then we have x1 double dot, and then x1 squared plus y1 squared over x1 squared plus y1 squared plus y2 double dot, and that's basically it. We can also cancel this and put a square root here, which gives us that 0 is equal to x1 double dot times x1 over the square root of x1 squared plus y1 squared plus y2 double dot. So remember, this is what we called A1, and this is what we called A2. And this thing, it looks a bit intimidating, but if you think about it, this is just the coordinate of x1. So it's x1 divided by the hypotenuse, which is cosine of theta. So this quantity here is cosine of theta, which ultimately gives us that 0 is equal to A1 cos theta plus A2. So we did all this complicated stuff, but thankfully it cancels out. Well, most of the stuff cancels, and we end up with this nice relationship. So I'm gonna use this as our third equation, and now we can find pretty much whatever we want. So I'm gonna start by substituting this into the equation for the second object. So let me bring both of them somewhere down there. So this was the equation for object 1, and then we had the equation for the second object, which is this one. So copy this here, and that's it. So this is equal to m2, and instead of A2 I'm going to write minus A1 cos theta, which is equal to minus m2 A1, and then instead of cos theta I'm just going to write what cos theta is, which is 0.8. So this is times 0.8. Okay, I think this might be a good moment to put in the numbers, just for the situation to simplify a bit more. So I'm gonna write this one first. So we have the coefficient of friction, which is 0.25. We have the mass of that first object, which is 30. I'm gonna use 10 for gravitational acceleration, just for simplification purposes, and then plus 0.4 times tension minus 0.8 times t, and this is equal to the mass of the object, which is 30 times a1. So let's work through this a bit more. We have this first term is 300 multiplied by 0.25, so that's just 75, plus we have 0.25 times 0.4, which is 0.1 t, minus 0.8 t, and this is equal to 30 a1. So 75 minus 0.7 t is 30 a1, and I think we're done for the first equation. And then for the second one, which is this here, let's rewrite it in terms of a1. So we have m to g, which is 150 minus t, is equal to minus, so I'm writing this part now, we have 0.8 times m2, so that's 15. 0.8 times 15 is minus 12a1. So that's it. We have two equations, two unknowns, so we can try solving them. So the tension is going to be 150 plus 12a1 if we rearrange. And then we sub this back in here. So we have 75 minus 0.7, 150 plus 12a1 is equal to 30a1. And then this becomes 75 minus 150 times 0.7 is 105, minus 12 times 0.7, this is 8.4 a1, is equal to 30 a1. So a1 will be equal to 75 minus 105, so this is minus 30 divided by 38, I don't know what happened, 38.4, which is minus 0.781 meters per second squared. So it actually makes sense if you think about it for this acceleration to be negative, because we assumed positive is going to the right, but clearly this block is going to go to the left, right? And the reason for that is because of this tension, which is pushing it to the left. Okay, so that's A1. And then we have to calculate, so the question was asking us to calculate this acceleration, which we're good, we did it. And then we can find the tension as well. You can find A2 if you want as an extra, but I'm not gonna bother with that. So the tension is going to be 150 plus 12 times A1, right? So 12 multiplied by minus 0.781, which is 12 times 0.781, and this should give us about 140.6 newtons. That's the tension, that's the acceleration, and that's everything that we did. So I think the trickiest part of this question, the free body diagram and Newton's laws were pretty easy to apply, but the tricky part, I think, was looking at the constrained motion between the two objects, and namely doing all this differentiation, which thankfully simplified to just this, and then that was our third equation. We used that together with Newton's laws to find the tension and the acceleration of object 1, and that's the end of the question.